Good morning. Welcome to Krishna's classroom. I am Krishna Kumar. I come before you with another episode of Riemann series today. If you recall, in the last lecture, we introduced alpha as step functions. And in that case, we found that the integral reduces to a finite or infinite series. Now this opens up a possibility that you can conceive a series also as an integral, or there could be a very unified approach for this problem. Now this is a marked advantage from this. Later on, we will consider a physical example where this kind of scenario emerges. That we will discuss later. But so a lot of versatility is brought into the concept of integration at this stage. I will make some remarks about this. But before that, we look at another special situation where we assume, of course, alpha is monotonically increasing and alpha derivative, that means we are assuming alpha is a differentiable function. Alpha derivative is Riemann integrable over A. Let f be a bounded real valued function on AB, then we can reduce the Riemann integral with respect to alpha as a Riemann integral. Now this is what we consider next. So we have the following theorem. So let me make the statement of the theorem. Assume alpha increases monotonically and alpha derivative belongs to R, that is Riemann integrable on A. That means we are assuming a certain amount of smoothness on alpha. Let f be a bounded real valued function on AB. Then this is the statement. Statement is f belongs to R alpha, that is Riemann integrable with respect to alpha, if and only if f alpha prime is Riemann integrable. So it is conditional. Okay. So certainly, depending on alpha prime, what that function is, you may have to have some restrictions on f to make it f alpha prime Riemann integrable. In this kind of scenario, we have also considered some examples. Highlight this point. What kind of conditions you will require. And f belongs to R alpha if and only f alpha prime belongs to R. This is what we want to prove. This is a necessary and sufficient condition. And in that case, integral a to b f d alpha is equal to integral a to b f of x alpha derivative of x. That is this. It becomes a conventional Riemann integral. Okay. So we give the proof of this. First of all, we will just decode what is given. What is given? What is given is alpha prime is Riemann integrable on AB. Okay, so what does it mean? So we are now writing this. Alpha prime belongs to R alpha. Belongs to R on the interval AB. It's a Riemann integral. Now this means the following. There exists, that is given epsilon, there exists a partition P of AB given by in our usual notation such that UP alpha prime minus LP is less than. So this is what is available. So we will make that this we shall be using. Now alpha prime, alpha is increases monotonically and alpha prime exists, and therefore by mean value theorem applied to alpha we have applying mean value theorem Okay, why do you want that actually? Because what you want to look at is two things. One, this one, what does it mean? This means you have UPF alpha on one side this is there, on the other side you have U P F alpha. Okay. So if you can prove that, these two are sufficiently close, okay, arbitrarily close for the partition P, then you can proceed to the limit, and you get the Riemann integrability of f with respect to alpha will give you UPF alpha minus LPF alpha less than epsilon, and from that you can go there, and if you are assuming this, then you can come to this, but you have to connect these two. That's the purpose. So to connect this purpose, connect these two terms, what are the terms that you have to look at? So let us look at this one. So this will give you, see, for instance, UPF alpha will be something like sigma mi delta alpha. This is UPF alpha, and this we have something like, say, sigma f of Si. What you have is delta. This is what. Okay, so we have to do some estimation of this part. So this will give you UPF alpha. You have to estimate this. This is what you want. And in this context, we apply the mean value theorem to, because you have on each xi minus 1 to xi, see alpha is given. So you have to have this one, alpha xi minus alpha minus 1. This is what you have to work with. And that, because alpha is differentiable, you can apply mean value theorem to get alpha prime times xi into xi minus 1. So you see, that is the transition from going from delta alpha I to delta xi, right, with a multiplying factor. So it's a natural thing to do. So that's what I wanted to say. So applying mean value theorem, to alpha on xi minus 1 xi, what we get, we have delta alpha I equal to alpha derivative Ei into delta xi. Because we are looking at this one, alpha xi minus alpha xi minus 1, and there is some point Ti. Now in the case of mean value theorem is a very typical existence theorem. Okay, and if you look at this result in analysis, you see that there is no way in which you can identify the particular point here. But all that the theorem tells, it's a very typical, all that the theorem says is there exists a Ti. It's also, it may not be unique, there may be several Ti's that exist, and if you look at the geometric proof of this, it will be very clear. Okay, so there is no way hitting at that particular Ti, but it says there exists. It's something like not exists. Okay, so you are not able to just literally pluck it and show you. So maybe in some examples you may be able to do, but in general there is no way in which you can identify the particular Ti. For some, so these are little things about analysis which one should know. So Ti belongs to xi minus 1 open interval xi minus 1 xi. So this is a typical existence. No way you are identifying that. Okay. This is true for I equal to 1. Now let us compute this. Okay. alpha prime belongs to R on AB. We have summation alpha prime SI minus alpha prime TI delta XI XI. Okay. Belongs to now put therefore you have sigma I equal to 1 to n f of Si delta alpha I. This is equal to sigma I equal to 1 to n. You replace this by this mean value theorem, the result of the mean value theorem. Then you get f of Ti X. So we have plugged in the delta alpha I has been replaced in this. Okay. Therefore, now we estimate this. Therefore, you have sigma I equal to 1 to n f Si delta alpha I minus. Now you see we have Si and Ti may not be the same. Okay. So we write this one. This is the sum corresponding to f belongs to R alpha, and this is the sum corresponding to f belongs to f alpha prime belongs to R. So this is equal to now this we estimate. What we do is we add these terms. See, FSI alpha prime SI and FSI alpha prime TI. So you add and subtract FSI alpha prime TI on this side with this term. Then what you get? You get an estimate for this, and you see that this will give you the following. So you have UPF alpha, this is UPF alpha, this is UPF alpha, and then you have brought in FSI alpha prime SI delta SI. Okay, and that is actually UP F alpha prime. So this part is but what we have is these two are equal. So you add this term and subtract from that. So if you do that, then this is what you get. You get UPF alpha. So you get UPF alpha is less than or equal to. What you have is you get a term which involves, see, the equality of these two are there. Okay. So when you add that term and subtract that term, then you get a portion where this result can be applied. So you just add and subtract and estimate. So there will be 4 terms, and then you make use of this result and then work with that. So that's a simple exercise. This is less than or equal to U P F alpha prime, and then you see that F is bounded by M. Therefore, epsilon comes from here. Okay, so you get this result. Now this is true for yeah. So theorem, let me just take out the thing for me. So one gets the following. In fact, I will just write this up. So what you have is, from this one estimated, you get sigma I equal to 1 to n f of Si delta alpha I is less than or equal to E F alpha prime plus n epsilon. Now this is true for all terms of Si belonging to xi minus 1 xi, which in turn implies U P F alpha is less than or equal to so this is one of the inequalities there. Now you know that by the same kind of argument, by the same type of argument, one gets U P F alpha prime minus, or E is less than or equal to now you also observe that when you replace P by any refinement of it, we still have the same inequality. True. The inequalities okay. Therefore, putting these two things together, what do you infer? One gets. Therefore, hence we have integral, that is the upper sum a to b closure f d alpha, that is coming from the infimum of UPF alpha minus integral a to b f alpha prime dx. This is less than. This is the inequality that you get. Therefore, since epsilon is arbitrary, for every epsilon this goes. Okay, we have integral a to b equal to integral a to b now this is about the upper integral. Now similarly we can work with the lower integral. Similarly, you work with LPF alpha and LP F alpha prime, and similarly with this. Therefore, you get working with the lower integral, we obtain the following, namely that one gets integral a to b so we get these two results. Now, of course, see, it's quite easy to work on. If f is Riemann integrable with respect to alpha, then you see that the upper integral of f d alpha is equal to the lower integral of f d alpha, which in turn implies the upper integral of f alpha prime equal to the lower integral of f alpha prime, and that implies the This is also Riemann integrable. Okay. So f alpha prime is Riemann integrable, and the Riemann integral is given by integral a to b f alpha prime. Okay. So you have the upper integral and the lower integral. The upper integral and lower integral are equal, then it gives you the integral. Similarly, on the other hand, if you were to assume f alpha prime is Riemann integrable on the interval ab, then you have the lower integral of f alpha prime equal to the lower integral of f alpha prime, or the upper integral of f alpha prime on ab. Therefore, you see that the lower integral of f with respect to alpha is equal to the upper integral of f with respect to alpha, which implies f is Riemann integrable with respect to alpha, and the Riemann integral is given by integral a to f t alpha. That's how the if and only if conditions. You assume one and prove the other. In both these cases, this equality is used. Okay, so now the statement of the theorem. Therefore, f belongs to R alpha implies integral a to b lower integral alpha, which in turn implies this is equal to the lower integral a to b f alpha prime dx equal to f a to b upper integral dx, and this implies and then naturally the Riemann integral of f with respect to alpha is the same as Riemann integral of f alpha prime on interval. Similarly, if you start with the assumption f alpha prime belongs to R, you can go backward, and then you can go backward here, then you can go back. So the two things are proved. Therefore, this completes the proof of the theorem. Okay? So these are the basic assumptions that we need. Alpha is increasing monotonically and alpha prime belongs to R, and f is assumed to be a bounded real valued function on AB. Then if f alpha prime is Riemann integrable, then f is Riemann integrable with respect to alpha. Conversely, if f is Riemann integrable with respect to alpha, then f alpha prime is Riemann integrable. That completes it. So the consequence of the theorem is that under favorable circumstances, you can convert the Riemann series integral to the ordinary Riemann integral. So Riemann conditions of alpha, you can convert integral a to b f t alpha to integral a to b f alpha prime dx. You should do this. And that often helps you computations. That's a justification. In there, of course, one has to look at the conditions on alpha. Some smoothness on alpha is essential. Okay, this alpha derivative should exist. Okay, now there are a few things that we look at. We make some observations from what we did so far. Make the following observations. So this is the first remark on this. The second remark is this is more general. We know that if alpha is purely a step function, then integral f d alpha is a finite or infinite. Finite or infinite. That shows how the series can be expressed in terms of an integral by a suitable introduction of a step function. This one. So if f has an integrable if alpha has an integrable derivative, that is what we have proved just now, then integral f dx f d alpha equal to integral that is integral f reduces to an ordinary integral. Now we can give a physical problem which essentially captures this whole thing, or it's very fascinating. Okay, so let us look at the following problem. Consider the problem of computing the moment of inertia of a wire with respect to an axis vertical to it through an endpoint. So you have a wire like this, something like 0 to 1 unit, and then there is a axis that is orthogonal to it. Now you see that this is actually a mass distribution. Okay. There's a distribution of mass on this wire. You look at it as a purely a mass distribution. So you consider an elementary mass dm at a distance x. Right. Then you see, consider the interval. So look at the mass contained in this interval 0 to x. Then what you have is the moment of inertia of this element is turns out to be x squared into dm. Now what you do is you integrate over from 0 to 1, you get the moment of inertia of the whole wire with respect to this, and m is a distribution of mass that you have on the wire. So which may vary from point to point depending on the density of the wire. Okay. So what you have? So the moment of inertia is m is given by integral 0 to 1 x squared dm. It is the distance x multiplied by this mass concentrated elementary mass that you have. And then what you are doing is you are just integrating it, because you are not assuming there's a constant or a uniform distribution of mass on mass. It could be a function of x. Mass could be a function of x. Okay, I'll give various details about this. Oh. So what you have, suppose mx denotes the mass contained in the interval zero x, then it's a function of x. That's what we have. Then m is in general a function of x. Now it varies from 0 to 1. Therefore, the total moment of inertia that you have is obtained by integrating this x squared dm over the interval 0 to 1. Therefore, you have now further assume the wire has a continuous density, say rho of x. Then we have the relation between the mass, the distribution of mass, and the density is that m derivative of x equal to rho of x. In that case, what you have is This implies zero to 1 x square into. So here you see the distribution of mass represented by m is a monotonically increasing function when you go from 0 to 1. Okay, and this is a Riemann Stieltjes integral. The Stieltjes measure given by m. Although I am just loosely using the word measure at that stage. Okay, which of course does what our alpha does. So it takes the place of alpha. And then you observe that because of this relation, that m derivative of x is equal to rho x, you get integral 0 to x square rho x dx. Rho is the density that you have. So there is a relation between density and the mass is that m derivative is equal to rho x. So this gives the usual integral of x square multiplied by m derivative. X square multiplied by m derivative dx. Now this is the content of this. Okay, right. Okay, let us look at another sentence. Suppose the mass distribution is discrete. Okay, it's not easy to imagine. Because you have a wire. Okay, you have, suppose mass is concentrated at various points x1, x2, etc. etc. Okay, suppose the wire is assumed to be masses mi concentrated at x side. Then what is that you get? See, if you come to x1, you have mass m1. At x2, you have mass m2. Therefore, the mass here is taken as m1. Then you have, it will define a kind of a step function. Mass distribution will form like a step function. And therefore, what one gets is that then the moment of inertia m is equal to sigma or integral, which will become a sum, integral xi square. I think it will become more intelligible. 1 to n or 1 to infinity or whatever. Depending on the mass distribution. Okay, now I'll give a more realistic picture. The realistic picture is the following. So you have a wire over the interval 0 to 1. Now at x1 you have a heavy bead. At x2 you have a heavy bead of mass m1, m2, etc. At xk you have something like nk. There's a wire also. There's a distribution of mass. Therefore, what is going to be mx? Mx up to this will be mx. And from here onwards, it is going to be mx plus m1 up to this. Okay? Because m itself is varying with x, and you have an m1 added to it, that point. And then from here onwards, there is a jump. So you have mx plus m2. So what you are getting is something like this. So this is the axis with respect to your calculating the moment of inertia. So you have got mx is this. Then at x1 you are getting a jump. So you start with mx1 plus m1. So you have another jump up to x2. Then so this will be mx plus m1 from here, and then you see you have another jump, so and so on. So eventually you get a jump between xk minus 1 and xk you take 1. So you have mk minus 1 and mk. So you get mx plus summation of my. Irony from 1 to k minus 1, and eventually from here it will be adding one more. So at this point it is going to be, mxi mxk plus sigma I equal to 1 to k. That will be the mass. So there is a jump there at every point. So this is your alpha that you are taking. And in that case, what you get? In that case, what you get is the following: m equal to integral 0 to 1 x square d alpha, or x square d alpha, or dm, and that turns out to be integral 0 to 1. You have two parts, a continuous and a discrete part of this. So you get x square, a smooth function d m tilde plus this is the smooth function that I am talking about, plus sigma I equal to 1 to k. You have xk square okay. So you see, this is due to the beads, the heavy beads that you have put on the wire. Okay. So this is a very typical example of how the Riemann series integral helps you to explain out the physical phenomena of moment of inertia of the wire. So another remark is that sometimes this alpha may not be differentiable at certain points. That also can be incorporated into the case. So for instance, what happens is that m is continuous. Say from this place to this place, it's a continuous differentiable function. But suddenly you see that it is continuous but no more differentiable. There's a sudden pickup of it. So you get a sort of step function thing which is not differentiable at certain points. So all these things can be incorporated into this language, and that is one big advantage of introducing Riemann series integral. And the motivation or the push came from physics in this. Now probably I want to make some more remarks about this. So we consider one example. An example of this type. Okay. So let us take the situation. See, we will take the interval 0 to 3. Break it up into 1, 2, and now we take an alpha which is possibly something like this. Maybe I draw a diagram. Draw the diagram properly. Lower pitch. Okay. So I take alpha x to be alpha x. I define as x square on the interval so the graph of the function is this. This is alpha on this interval. Now from 1 to 2 I define alpha to be a constant. So I take alpha x to be equal to 1 from 1 to okay. There I give a jump to it. If you take a jump and say there's a height of 1, so it starts at 2. And then what I do is I replace the function by c x square is 4 by the same, so I replace it by x square minus 2. So x square minus 2 at 2 is 4 minus 2, that is 2. So it starts from here, and then here it goes up to 3. You have 9 minus 2, that is 7. Goes up to 2, 3, 4, 5, 6, 7. So it just goes like this. This is the function. So you take it as belonging to 2, 3. So there is a jump discontinuity at that point. Okay. So this is your alpha. This is the graph of alpha. 7, 6, 5, 4, 3, 2. Okay. This is y equal to x square minus 2. This is y equal to x square, and this is y equal to. So there is a jump discontinuity. Okay. Now what one does is we introduce a function f. Okay. Now what I want to impress upon you is see See, you have the integral from 0 to 3 of, this is what you want to calculate. That, of course, you can split it up into integral 0 to 1 f d of x square plus integral 1 to 2 of f constant function, that interval. And then what you have, see, because alpha has a jump here, some contribution comes to the integral. So you have also a integration from 2 to 2. What you have a jump discontinuity. So you get here f of, I assume f is continuous at 2. f2 into 1, the jump discontinuity, plus integral 2 to 3 How does this term come? Okay. So if you split it up, if you break it up into if you partition this interval 0 to 3, you take a partition of this into 2 minus epsilon 2 plus very small epsilon, and then you have a partition from, you can have a partition, it will give you the usual Riemann Stieltjes integral on this, and then you can have a single partition from here to here, because it is immaterial, because what you have is alpha a minus alpha b, for a and b belonging to this interval is equal to 0. It's 1 minus 1 by 2. That is 0. So nothing matters there, but this matters on this side and on this side. So you have got alpha 2 minus epsilon equal to 1, and alpha 2 plus epsilon is equal to 1. You have 2 plus epsilon whole square minus 2. So what you get here, the difference of these two will be, so here there will be a sum, okay. So if you take the supreme on this interval, the sum will consist of, see, so if I take this as xi minus 1 to xi, so I have the particular sum coming out to be f of di, where di belongs to xi minus 1 to xi, f is assumed to be continuous, multiplied by alpha 2 plus epsilon minus alpha 2 minus epsilon. Let us compute this. This is equal to, so you have the other sum. So this term stands out, and you have the other sum. Okay. So this sum, this term, let us take for term. So this is going to be f of pi. This part will be 2 plus epsilon whole square will be 4 plus 4 epsilon plus epsilon square minus 2 okay, minus 4. So this term, so this is equal to sigma of the other terms plus FTI into you get epsilon square plus 4 epsilon plus 1. Okay, so that's the sum that you get. And now you let this xi xi minus 1 go to xi, or you know, xi minus 1 and xi both go to 2. Then what you get? Because we assume f is continuous. Assume f is continuous. That's equal to. In that case, this particular term then as epsilon tends to 0, what is that term? That term is f of pi into epsilon square plus 4 epsilon plus 1 goes to f of 2 goes to epsilon goes to 0, f of pi goes to 0. Now you see that here pi is between 2 minus epsilon to 2 plus. That's what you get. So this is what you get. So you get f of 2. So it's actually f of 2 into 1. You give a bigger jump here, and you get a much bigger value. Okay? Right. So what more we have to see? See, we are assuming, if you are assuming f to be continuous at 2, then the integral will exist. If f is not assumed to be continuous at 2, then the integral won't exist. At 2, the integral exists because you have the problem of mi minus mi into alpha around point 2. Okay, so xi equal to, this cannot be made arbitrarily small, so that your cannot be made arbitrarily small. So the upper sum and the lower sum, you cannot get a partition for which upper sum minus lower sum will be less than. This is the problem. On the other hand, you also see here, suppose you stay away from 0. Okay. So consider f on the interval 1 plus epsilon to 2 minus epsilon. It makes no contribution at all from there. Why? Because alpha is a constant. No contribution where epsilon is formless. Then there is no contribution to the integral from this part of the sum. On interval 1 plus epsilon to 2 minus. There is no contribution at all there. Therefore, the contribution from there is 0. All that one needs to assume is that f is bounded. Because that sum, if you work out, it is going to be 0 because the multiplying factor. So you have got something like, so on that portion, you see that alpha xi to alpha xi and alpha xi minus 1 and alpha xi take the same value. Okay, equal to 1. So that difference is 0. It is immaterial what f is as long as it is bounded. Okay, right? And that also tells you something more. Even if you choose the function to be rather violently oscillating on that. For example, I take this as, so suppose f is given by the following function, that is let me chi of q intersection and take fx as the characteristic function of the rational intersection interval 1 minus epsilon to 2 minus epsilon what does it say? It says that on the interval 1 plus epsilon to 2 minus epsilon, and just staying clear from these ends for convenience, not to have any problems coming up from that, because there is a continuity problem here at this point. At this point there is no problem because alpha is continuous, there will be no problem. So if I take this function to be this one, what is this function? This function is the Dirichlet function that you see. See, it is 1 at all rational points here and 0 at all irrational points there. So left to itself, it is not a Riemann integrable function. It doesn't matter, it is bounded function. Okay. Even if your f has a portion which is not Riemann integrable on some interval of the place where alpha is a constant, it is immaterial. The integral will exist. Okay. So all that you need is, you have to be careful on the other parts of it. In that case, what is the integral that you get? The integral that you get with respect to alpha of f is going to be, so the integral will be essentially this. Zero to 1 fx at d of x square, which I can replace. And I don't have any contribution coming from 1 to 2, but I get a contribution from 2. What is that? I get f2, the value of the function at 2, plus integral 2 to 3 fx d of square root. Okay. Now I can use the previous theorem because these are nice functions. Therefore I can write this as integral 0 to 1 fx 2x dx. Here I can again get from 2 to 3 fx 2x dx. So this 2 will not matter. So this is the rate of change of that matters. Okay. Okay, I think that's a nice place where we can stop this talk, and it gives some more insight into the particular alpha that you are taking. Once you, what is the advantage that you get by going from usual Riemann integration to Stieltjes integration? Okay, this is a very smooth transition from Riemann integration to Lebesgue integration. Just a path. Now here we could vary the measure of intervals. Once again, I want to emphasize one point. Still in Riemann Stieltjes integral, we are only talking about the length of intervals. Okay? We are only talking about length of intervals. Maybe in my next lecture, before I start with the change of variables topic, I will make some remarks about it. Okay. Thank you.